Hello, I'm Ben Baumgartner from Lockheed Martin in Sunnyvale, California. I am from Process Control Engineering. Our responsibility is electrostatic discharge protection for the facility here. What we're going to do today is go through ESD training along with some demonstrations, and we have here equipment to help you understand the principles of ESD, and here's the paraphernalia we have to give you some interesting demonstrations later on in this presentation. We're going to cover here is what is ESD. We'll define it. We'll tell you what EOS is, what their sources are. Then we'll go on to the controls here at Lockheed Martin, and this stands for Lockheed Martin Missiles and Space. We will then show you some damage mechanisms, and the final portion of this will be covering what our requirements are for superstations, which are for the very sensitive field sensitive devices that we are having in our facility at this time. First, let's go through some definitions so everybody knows what we're talking about. When we talk about EOS, this is electrical overstress, and that is damage due to exceeding the electrical capabilities of a device. This is when you damage something by overstressing it, you will take and exceed its parameters. If you change its parameters or if you destroy it completely, that is electrical overstress. Electrical overstress can be things like taking a 12-volt car bulb and putting it on 110 volts. It will act like the old-time flash bulb. That is electrical overstress. It could be from putting your battery in your electrical device backward. There are a lot of things that will cause electrical overstress. Electrostatic discharge, that is a specific event, and that event results in a sudden release of energy, generally in a very short period of time. Because this is a specific definition, by definition is a subset of electrical overstress. There's another term we use quite often. That's called tribocharging. Some people say triboelectricity. There are a lot of words using the word tribo in front of it. And tribocharge or triboelectricity is due to charge separating from the contact of two materials. Whenever you have two materials contacting each other, the charge is separated, and when you separate the materials, now you will be able to see an electrostatic field, and you've increased the potential for it to do damage. Some additional terms that we'll be using is discharge or ESD damage, and that can be arrived at by a transfer of charge due to an arc. That's the type of thing that you can feel sometimes when you slide out of your car and touch the car door. Transfer by contact, which you normally don't feel. You touch things when you have a slight voltage on it, you will not feel that transfer. And the hardest to understand and does damage only to certain types of devices is the transfer due to induced fields. We will cover all those things. The induced voltage is electrostatic charge caused by polarization. There are two devices in the electrostatic protection world that we have to be concerned about, and that is the voltage-sensitive device and the energy-sensitive device. The voltage-sensitive device is damaged by electrostatic fields, or can be damaged by electrostatic fields, and is definitely damaged by a direct discharge, this transfer by an arc. The energy-sensitive device is damaged only by a direct discharge or contact. In other words, you have to put energy in to destroy the device. Where in the device that's field sensitive, you do not have to put in a lot of energy to destroy it or even damage it. There are some other terms that we need to know that we use quite regularly, and Everybody understands what insulative material is. Well, we have a definition for that. It's a very high resistance material that does not dissipate charge. In other words, if you charge up a piece of Teflon, the charge will stay for a very long period of time because it has an extremely high resistance. In electrostatic discharge protection, we have a material called dissipative, and this term is used throughout in the terms of protection for many types of materials, devices, and etc. The resistance of this material results in a slow discharge of energy, and that is the ideal situation for protective materials. Of course, there are conductive materials. Metals are conductive. There's a lot of other materials loaded with carbon that are conductive, and the resistance of this material results in a fast discharge, which is generally not what we're wanting. In terms of all these insulative, dissipative, conductive, we use the definition of conductive or conductivity as any path, as a path for any amount of current. Therefore, if you have an insulative material, it has a resistive path to ground. At extremely high will not transfer much current. Dissipative will transfer more current, and conductive will transfer a lot of current. So we will use the term conductive for dissipative materials and even for insulative materials, and you have to understand the context it's being used in. Conductivity is an engineering term that has specific definition, but it will be used here interchangeably with conductive and ignoring the definition that the engineers use. We talked about direct discharge. An arc is a direct discharge between two objects. It can come from or be exhibited by two different modes. A corona discharge is a local discharge of electrons. You won't have a blue color spark going between the two objects. You'll only see a little glow on the end of the needle, and ionizers use this corona discharge. If you have a very high voltage on a person, you might have some corona discharge before you have a arc, which is a concentrated flow. This is the one you hear and feel if it's high enough. Contact, of course, if you touch something and you have a voltage on it and you have resistances that allow that charge to be transferred, by contact you will transfer charge that you won't see or hear anything, but you will still be able to damage devices. We're going to represent a person by a sphere that has a certain charge on it. And if this person touches a device, they can have an arc going to the device, and if the device is grounded, the charge will go to ground. Here this is represented in this diagram by an arc to a device. It's represented by a resistance going to ground. Whenever there is an arc or contact, current will flow through this device, and the current causes the heating, which causes the damage if the conditions are right. The contact of the person to the device is a much lower resistance contact, but it's generally a lower voltage, so it can or cannot be dangerous to the device. We talked about tribocharging. This phenomenon needs to be explained a little bit. There are two types of charging mechanisms depending on what is being moved. If you look at charge transfer based on an insulative material that is the base here, and you have a conductive block, you have one type of transfer. If you have a conductive material and an insulative block moving on there, you have another type of transfer. What this tells you is that if you have charge transferred the minute you have contact, and you slide this along an insulative material, this charge cannot move, because we said insulative materials have a very high resistance. Therefore, the charge doesn't move down here. Charge can keep transferring off this surface onto that surface, and eventually, when we take and lift it off here, we have a high field on this metal object. Excuse me, on that one up there. If we take an insulator and slide it along, then the conductor here allows charge to move, so the charge will move along. It moves underneath here, and when you move the insulator up, you will have a charge on the insulator. You will also have a charge on the metal. These charges are equal and opposite, but there won't be any charge back on the metal here until you lift it off, and then charge will distribute itself back over again on the metal portion. You notice ground is not involved in here. Ground, a contact to a ground by the metal does not take and prevent tribocharging. What it does do is take the charge off that is put on the device. We will go over to the table now, and we'll pick up some devices to show you that in a more explicit fashion. First, we must define what a capacitor is and understand how it stores energy. If you have two conductive surfaces with an insulator between them, which can be air, this is a capacitor. The capacitor has the ability to accept charge. When charge is placed on the capacitor, it raises the potential of these two surfaces. This creates a strong field between the two surfaces. This strong field, when it gets strong enough, is what causes the discharge between surfaces. It does the damage because of the amount of energy stored. The energy storage can be looked on as like a battery. The more the energy is stored, the greater the potential for doing damage for electronic devices. Now, let's see how this relates to tribocharging and capacitance. To understand tribocharging, we have to understand the concept of capacitance. What I have here is two metal plates. These two metal plates have capacitance between each other and a certain value. But one metal plate also has capacitance that people don't realize. This capacitance, the other metal plate, is the world around them. It's me, it's the floor, it's the ceiling. So one object can have a capacitance. And in the tribocharging instance where we talked before about the surface being insulative, I have a piece of Teflon here, and to illustrate that example, when I put this metal plate down on the Teflon, it has picked up charge. If I slide this along, as I explained earlier, the charge will stay on the insulator. Now when I lift it up, this has a capacitance, and there's a field line going back to the Teflon, back to me, back to the world. It's this field that is a potential source of damage to electronic devices. If I assume now that this is a metal surface and this is Teflon, when I put it down, I have the same two contact surfaces and electrons will be transferred. But this time, if this white sheet is a good conductor and I slide it along, the charge will move along underneath it, and therefore the same charge that I had over in this end of the piece of metal will be underneath it here, and I lift it up, and now there's charge on this insulator. There's one more thing that we have to address in relationship to tribocharging, and that is humidity. The issue of humidity affects the tribocharging in materials when there's a lot of moisture in the air. For example, if you have a insulative material and the moisture in the air settles on it, there is a phenomenon called bleed back. The charge now runs along the surface as it does with a conductive piece of material, and this reduces the amount of tribocharging that you see. Therefore, on very dry days, the surfaces will be very dry and have a high resistance. This allows the charge separation to stay where it's at and increases the amount of tribocharge. On moist days, the tribocharging is much less because of the bleed back phenomenon. Therefore, on dry days, you have to be extremely careful in handling material so you do not charge up the material and cause a hazard. Our program is designed to protect you from ESD in all humidities. To continue on with tribocharging, we need to talk about charge separation. If we take a ESD bag and put it on conformal coating, we have charge separation. In other words, tribocharging or triboelectrification. application. If we take and raise this bag off of that conformal coating, we have charge separation, and as I said earlier, once you separate those two objects, you begin to see a field. To demonstrate that, we have a piece of equipment which I will show you shortly that measures the charge on this system. And when you set the bag down, you will have very little voltage seen on the system. The minute you lift the bag off the surface here, you will see a charge. When you put the bag down again, the charge is close together, therefore the fields are not available to the rest of the world, and now you will go back to the 0 point. And you can lift it off and it'll charge up again, so you have this continual up and down as voltage as you move it around. In effect, you're changing the capacitance of this object in space, and the fields are coming from the material out into the world, which is the thing that is dangerous for ESD sensitive devices. I will now explain the equipment that makes the measurement over here that's on the table. This is the main unit of the electrometer, and the electronics in here decides what voltage it has to provide to the electrometer head. Once it makes that decision and outputs on the meter, we also are recording it on the chart recorder here, and we have 0 volts here at the center. It goes up to plus 2 kV, which is 2 kilovolts, and minus 2 kV, and now we see an output of what the voltage is on the electrometer head. Now we need to explain how the electrometer is calibrated. The electrometer system is calibrated with a power supply, which we have here, and this power supply is connected to what I call a resistive wand, which is a 10 to the 8th ohm resistor to prevent people from getting electrocuted from a high current. And we can show the calibration now by setting this power supply at 2 kV, and we come over here and touch the electrometer head, and now when I flip it on, it goes to minus 2 kV. If I turn the switch to plus, it goes to 2 kV plus, and if I remove the wand, that voltage stays there. That is the electrostatic voltage, and you notice that I can touch ground on the case here and put my finger on the plate and ground that voltage without any sensation of charge. This is how we calibrate the system, and we have a scale here in which we can change it to plus or minus 200 volts, and we'll be doing that during the demonstration. Now that we've explained the instrumentation for measuring electrostatic charge, let's go back to our charge separation demonstration, where we're going to show that when you separate materials, the charge shows up and then disappears again. Now we'll go over to the electrometer, and we have here a ESD bag and a conformal coating that's on the plate, and I will put my wrist strap on to ground myself, and I will now take and push down on the ESD bag and the conformal coating to make sure there's contact, and when I lift it, you'll see there's a little bit of charge. Now if we change the scale to a 200 volt scale, you'll see that there's charge, and if I put the bag down, the charge goes to 0 apparently, but it's still separated because I lift it up and the charge is back again. So you see, any time that you take a metallized bag with a conformal coating against an insulator, we have this tribocharging effect, and we have the charge separation, and that effect is present in any of your materials at your workstations. Now for the next subject of induced charge. The factors with induced charge are that the person, as we've talked about earlier, has some capacitance, and as he gets closer to a device, he will induce more charge in the device. This is represented by this capacitance C here, and as we said earlier, any object in space has capacitance. the capacitive coupling is determines the amount of charge induced into the device. In other words, the amount of polarization. The capacitance is larger because the area is larger, then more charge will be induced in the device. If the capacitance is a greater distance away, there will be less induced voltage in the device. So the two factors are area of the surface that is coupled into the device and the distance that the area is away from the device. When you couple into a device here that has a resistance, what happens is charge will come up from ground to satisfy the charges that you are inducing in here. That's polarization. When that charge runs through the device, it will cause a little bit of heat. If this device is an energy-sensitive device, as we explained earlier, it is not sensitive to fields that are induced by this polarization effect. Therefore, that device won't be hurt. If we have here extremely high resistance and we induce a field in this, current starts to go through that device. But if the resistance is an extremely large number, we're developing an extremely high voltage across that, and with the voltage-sensitive devices, this device is essentially an insulator, and the insulation will break down. That is field-induced damage on a voltage-sensitive device. We have a demonstration here which will demonstrate the fact that you can charge an object from a styrofoam cup and induce a charge in the object. What we have is a conductive sphere which will be a gold-plated ping-pong ball, and we will put this sphere and drop it into a charged styrofoam cup. When we drop it onto the electrometer plate to see if there's any charge gained by the gold-plated ball, when it bounces off of here, you'll see that the needle doesn't move. If we take the gold-plated ball, place it in the cup that's still having the same charge, but we maintain a ground contact, and then drop it on the plate, you'll see there's a charge. Now, why is this important? What this tells you is that anytime you induce a charge on a circuit board and you ground a conductor on that circuit board, you can induce a charge in it. So this leads to the conclusion that you want to maintain very little contact with a circuit board. You want to minimize that contact. And we will go over here and demonstrate this by the use of a styrofoam cup and a gold ball. And first I have to ground myself. And we'll check that we're still at the 2,000 volt range. I will rub the cup. And part of this principle is to demonstrate that the cup has a lot of charge on it. And you notice the cup is sitting on the electrometer. The charge is negative. It's even gone off scale. And when I lift it off, it comes back to zero. This means that when I place the gold ball in the cup, there's not going to be any charge coming off an insulator. This is a very important fact to recognize when you were talking about charged surfaces and the distance away from a sensitive part. I'll now take the gold-plated ball. I will drop it into the cup at a distance, and now I will take and try to drop it onto the cup, and you see there is very little change in charge. I will now take the gold-plated ball, place it in the cup while I maintain contact with it, and now I have induced a charge into that gold-plated ball that's available through my wrist strap and has come up onto the gold-plated ball. Now, when I roll the ball out, it has picked up charge, showing that I can induce a charge in a grounded object if I am in a strong field. And this is a principle that you have to watch for when you're out in the shop and try to maintain very little contact to tribocharge surfaces of circuit boards. We have just seen that grounding doesn't necessarily give you complete protection. Nevertheless, we use grounding as a very important tool in keeping static charges from developing at a workstation. We will cover in the next few slides the use of an ESD common point ground, describe the third wire on the AC outlet and its relationship to ESD grounding, talk about vehicle ground, building grounds, where they're attached, equipment grounding and how that is important, and soldering iron grounding, which is at a lot of the stations where equipment is assembled. Now let's talk about earth ground and grounding issues. Many people believe that you need a earth ground at every station. That is not necessary. A grounding rod has resistance, as you see from this chart. It is not 0 ohms to ground. The grounding resistance depends on the length of the rod, moisture, and other factors. What we do at a workstation is we use the third wire ground as the ground point to establish the equal potential at the workstation, and this is connected back through earth where the power company supplies the incoming power at the building. It's very important that the ground be maintained, and this is what the process control certification does. I have here a little checker that can be bought at hardware stores, and if we plug this in, you'll see 2 green lights. This tells us that the equipment grounding conductor is connected, and it also says that the polarity of the neutral is proper. These are important items because there are a lot of times when a socket is miswired or there is no connection. This connection is the point that the station uses to ground charge at the location, and that is all that is necessary for the proper ESD station control of ESD. Personnel grounding is the most important way of keeping ESD from damaging parts at a workstation. The wrist strap is connected to the common point, and we have a wrist strap here that has a certification sticker on it. That is very important that you use a proper wrist strap that has been improved. We have leg straps that are used in certain areas. They're only good if you have an ESD floor, and that ESD floor must be certified. The wrist strap connection can be made to the vehicle. If you have a vehicle that is in an assembly area, that vehicle is grounded to the equipment grounding conductor through the building ground. We never allow contact to occur from an ungrounded person because that person may place charge on the person that is grounded, and we will explain that later in some demonstrations. If you have to make contact, if you have to deliver something to a person, set it on the ESD workstation. That takes the charge off of it, and therefore, if you're not grounded, you won't have any problem with putting charge in the person that is working on equipment that may be touching a sensitive device. This slide shows schematically what goes on at a workstation. We have a table mat that can have a resistor in there to limit the current going to the common point, but it's sufficient to drain off any charge from equipment or any tools you put on there. It is connected to the equipment grounding conductor. If you have a shelf that you need, it is also connected to that point. We do not use shelves here very much because we believe we should package the device if we're putting it up for storage for any length of time. The wrist strap connections here go to this point, and all that is connected to the equipment grounding conductor, which is connected to the building. The floor mat here is connected to that point. The only thing that isn't connected is the ESD floor, which is connected to the equipment grounding conductor through the building connection. This equipment grounding conductor is at the same potential as the building ground, and therefore you do not have potential differences between any of these objects or pieces of equipment if they're all connected up and certified. We talked about charge being transferred from an ungrounded person to a grounded person. The wrist strap has a resistance in it to ground, and this resistance limits the current that is going to ground. It also has the effect of making the charge placed on a person take a little while to get to ground. So if we demonstrate here that a person will transfer charge from one person to another, that charge is instantaneously transferred because there is very little resistance between two people, where the wrist strap to ground of the grounded person has a 1 megohm resistor in it. Therefore, because the resistance is low, when one person makes contact with another, that voltage is transferred over to the other person because the charge transfers extremely rapidly. What we're going to do is charge up a person with an electrometer, and we're going to charge him up to 2 kV, and this person represents about 150 picofarads capacitance, can be more or less. He goes over and touches another person. What we have here is 150 and 150 picofarads. The sum of those is 300 picofarads. So by this equation, charge is equal to the capacitance times the voltage. Means that if we have a charge on this person and we transfer, the capacitance here now has doubled. That means the voltage has to go approximately to 1/2 of that to equal the same charge. Now we'll go over and do that demonstration. Now let's demonstrate this charge transfer between two people. I will take and remove the electrometer plate, place my wrist strap into the electrometer, and charge myself up to 2,000 volts. Now we'll ask for a volunteer to come in and touch me, and you'll see that the charge is approximately split between us, and the resultant voltage is nearly half of what we had when we started this experiment. What this shows is that the charge is transferred from one person to another very quickly. If that person is a grounded person at a workstation, that voltage will be on that person before the wrist strap carries the voltage away. At the workstation, the third wire ground, besides being used to ground the person, is also used to ground electrical equipment. Electrical equipment can have leakage currents, and that's really an electrical overstress problem. An example is a soldering iron. A soldering iron has capacitances that couple voltage into the equipment, and since the equipment uses the third wire ground here to ground that equipment, that current does not show up as a voltage should some small current leak across things in the equipment. The resistance is checked on the soldering iron, and you have to check that depending on your particular programs and the types of irons that you have. And that assures that the iron will not cause any damage to sensitive components. Another important part of ESD protection is packaging. We have some packaging principles that we follow. We'll talk about the types of packaging material, we'll define what a primary package is, and we'll talk about the labeling that needs to be on packaging to identify that there's an ESD sensitive part in there. And we'll talk about the packaging of very sensitive devices. The MIL B 81705 specification has established the different classes of packaging material. The first type is a waterproof electrostatic packaging that has a metal foil. It has strength materials built into it. It has a dissipative polyethylene material on the inside. The metal foil on the material provides excellent protection from electrostatic fields. This is a type of packaging. You can see the marks on the edge here showing the strength. The inside has a dissipative coating and satisfies the requirements for the military specification. The second type of packaging is the Class 2, Type 2 packaging, and that is a dissipative pink polyethylene. It can have a dissipative coating on the surface. Most of the polyethylene material that's out there has a surfactant milled into the surface, and this bleeds to the surface, it picks up moisture, and this is what gives it its dissipative properties. This is the pink polyethylene material. It allows it to be sealed in this, what makes it into bags. They take material, flat material, seal it on the edge. It is transparent. It is not highly capable of shielding fields, but it does protect very well against direct discharges. The third type, the Type 3 or Class 3, is a metallized foil bag. It may have one or two layers, generally just one layer. It has different types of materials built into it for strength. It is also fairly transparent. This bag, because of its metallization, is conductive and will shield somewhat compared to the pink poly, but it does not really protect voltage-sensitive devices. The primary protective packaging is defined as the innermost package that fully protects a device. There are many forms of bags and types of packaging that can do that. The tote boxes here are a primary package if they're enclosed. The lid has to be on them for them to be a primary package. The electronic equipment box that has the electronics in it, if it's a metal box with the connector caps in place, is also a primary package. And there are other carriers and blister packs that can be used for electronic packaging, and you have to determine whether those are sufficient for giving primary protection. The packaging is part of the protection and handling of material by using proper packaging needs to be followed. If you don't handle material when you have it improperly packaged, if you handle material that's improperly packaged, you can damage it. The material has to be packaged properly before you can handle it. Conductive materials such as the Type 1 and Type 3, that is the metal foil and the metallized bag, are very conductive and need to be removed from the certified work surface after you remove the part from them to work on them. Also, a very important handling procedure is minimize the contact on insulators, because you can tribocharge the insulators where you touch. The handling of cables and connecting cables need to be done according to the specifications. The engineering must be aware of the problems here and need to specify how that is done. All the packaging that you handle in terms of ESD needs to be identified that there is sensitive devices in them, and you need to follow the proper specifications. Now to do a demonstration relating to handling issues. We said that cables connected up to a box, when you remove the proper packaging, the connector cover, and you connect up a cable, is very important. We have here a piece of material that has an insulator on one side and a copper conductor on the other side. What I'm going to do is use this to represent a coaxial conductor that is covered with an insulator on the outside, and the electrometer will be the shield around the coax. If I set this down here, now I have a conductor going across a surface that is the outer shield of a cable. I have myself grounded. I will charge up that strip to approximately 2,000 volts, and then I'll ground the outer shell, which represents the coax cable outer conductor. And you can see that if I move that conductor now by changing its position on Earth, I have taken and induced a charge in it. It's very difficult to get charges off of cables. Grounding one point or the other can transfer charge back and forth. This is why engineering has to be involved in procedures for connecting cables up to boxes. We said in the outline we were going to cover damage mechanisms. And to do that, we need to define again what voltage sensitive and energy sensitive devices are. Voltage sensitive is the most sensitive device and can be damaged by fields. And it's the one we worry about the most. The energy sensitive devices are fairly easy to protect. The damage to devices by electrostatic fields will be covered when we explain what these devices are, and we'll show you that damage by direct discharge can come from charged surfaces. Voltage sensitive device, as we said, is the one that will be damaged by a field. You do not have to make contact with the device. A voltage sensitive device can be thought of as analogous to a string, and the tensile strength of the string is a failure of the gate oxide. Turns out that a voltage sensitive device is an unprotected gate oxide MOS device. There are not very many of these devices around, but they're the hardest to protect and the ones we have to make sure that they do not get through the system without proper protection. The gate oxide will not allow any charge to go through it. We said previously that if you had an induced field into this high insulator, you would develop a very small current through it, and a very small current through a high resistance will develop a high voltage, and you'll have a breakdown. There's a narrow range of this failure of the gate oxide, and the breakdown occurs in a very short period of time. Heat conduction is not a factor. The breakdown is analogous to a piece of string. We take a piece of string and we put pressure on it. It doesn't fail. I cannot fail it just a little bit. It either breaks or it doesn't break. That is the narrow range of a voltage sensitive device, and this can be caused by charged surfaces being brought near a device, and if the capacitance is sufficient to induce a voltage that goes beyond the breakdown of the gate oxide, the device will be damaged. The other type of device is an energy sensitive device. This device represents the vast majority of devices that are out in the electronic world. The energy sensitive device is a semiconductor junction, such as a diode or transistor, and MOS devices can be connected up to look like a semiconductor junction diode. The reason for considering a diode is that any device hooked up in this manner will let current go through it in the forward and the reverse direction. This is what makes it insensitive to electrostatic fields, because the device is damaged by heating of the junction when a vast amount of current goes through in a very short period of time. It's the applied energy that is similar to melting of solder that does the damage. The heat that is applied very rapidly exceeds the dissipation rate of the device. The device will rise to a temperature which will destroy the junction. The damage is related to the human body model HBM energy classification. And we can look at this device as being a piece of solder or a piece of metal, and it's the amount of heat we apply. If we take a very thin rod and we take a match and we strike it, now we have a flame here, and we bring the rod It's very small. It will heat up rapidly and even become red hot. If we take a larger rod and place it in there, it takes far more energy to heat this rod and bring it up to the melting point. That is what is the difference between the gate oxide and which is a voltage sensitive device, sensitive to fields, and the energy device, which is sensitive to a direct discharge, which is a rapid transfer of energy. If we look at some failures of gate oxide, we can see that this failure can be created by handling, because we can exceed the voltage range of the device. And we also can see that we've had damage devices by improperly adjusted or ionizers that have very long pulse rates or have gone bad by putting out one polarity. You'll see the damage here shows a little melt zone, which may be hard to see on the video, and it pokes through the oxide either at the edge or in the center of the gate oxide of this device. This device was a 160 volt device, and it was able to be blown by handling, following all the procedures. The device was also able to be blown by a bad ionizer. This is why ionizers need to be certified by process control. Here is the protection circuit that we will do the demo on. We'll use our electrometer again, and we will bring a styrofoam cup down on the electrometer, and as you saw, that will raise the voltage on the electrometer plate, induce a voltage on it. We take it away, it'll come back to zero. Now when we connect up the plate of the electrometer to a neon bulb, and we apply the same induced voltage by placing a cup on the electrometer plate, it will go up to approximately 60 volts of the neon bulb. When you take the cup away, it will go in a negative direction, and we can do this repeatedly. The protection circuit's being exercised and the device is protected and not damaged. This is the demonstration of the protection circuit. I'll ground myself and take our styrofoam cup, charge it up again, and show you that it will drive the electrometer off scale. And now what I will do is take our protection circuit and connect it up to the electrometer. This represents a circuit between the input pins of a device or any protection circuit on a trace. And what we have here now is that this represents the transistor input pin. This represents the ground of the board that the transistor is on. And we'll take our cup and we'll go down here, and you'll see there's very little change in voltage. We will now go down to the 200 volt scale, and you should be able to see the 60 volt up and down charge change. My wrist strap just dropped out, or I didn't connect it. I will connect it up again to make sure the experiment is right. And you see, I can't drive it off scale. The minute I disconnect my protection circuit, I'm driving it far off scale. And that's why most electronic circuits at workstations, if you follow all the rules, will be protected, because you will always develop some tribocharging, but this circuit prevents you from damaging any devices. You still have to follow the rules of grounding yourself and proper packaging and handling. To understand how small these devices are, this little speck you see here is a IC, that integrated circuit, that has many transistors on it. These transistors, for the most part, have protection circuits built into them. To give you a better view of this, you will see this chip with the little tabs on the end of it that are 5 mils across, and the little white spot coming across is a gray hair that is put on that, which is about 2.5 mils or 2.5 thousandths in diameter. You can hardly see the transistors, but you can see all the interconnecting circuits for this particular device. This is fairly old technology. Present-day technology now is down so small that you would not be able to view it optically. You'd have to view it with electron microscope. And these devices have gotten so small, though they've gotten more sensitive, the protection circuits have to be there and have gotten very strong to protect the devices. We're going to conclude with some demonstrations that we want you to take back to the workplace that are important for ESD protection. And it will also impress you on the awareness that you need to keep for protecting ESD sensitive products. I've grounded myself in a wrist strap. I have a ESD glove on, which is dissipative or conductive depending on the brand. It will discharge something that you have a charge on, but it also will create charge on conformal coated or fiberglass circuit boards or a lot of other objects that you may touch. To show this, we have a radio here. It is on. It's turned off station, so you won't hear the station, but you will hear the charging going on as you rub this surface. Now, if we take a piece of metallized material and we take the Teflon material and charge it with the wool, you'll hear the wool also charges it like the glove. We will raise it off the surface there and bring the metallized bag to it, and you hear the discharge. We'll try that again. Whoops. You hear a series of discharges. Now we'll repeat the experiment with charging it, and we'll use a piece of dissipative material. This is pink poly material, and will come into the surface, and you do not hear the discharge that you do with metallized materials, to show that you need to remove the metallized materials from the workplace. We saw that an ESD glove would tribocharge Teflon, but it will also tribocharge the items in your workplace, as we stated earlier. Over here we are coming to an electrometer, and I'll check that we're at the 2,000 volt scale, and we are. And now, rubbing a piece of metal, we don't see any voltage. And if we charge the plate up to 2,000 volts, you'll see that it discharges it fairly rapidly. If we take the metal electrode out and put in its place a metal electrode that's covered with conformal coating, and now we rub this surface, you'll see that we generate voltage very easily. And you can see the palm of the hand adding onto that surface generates a lot of charge. I wouldn't generate as much if I was touching a very small point. If I put a fiberglass board in there, we can generate charge also. And this is what the materials are made of in your ESD that you need to protect for ESD. We'll take a piece of wire, put it in our electrometer, and with my glove again I will show you that you can generate voltages on a 6-inch piece of wire. If I discharge it to 0, you think the charge has gone away. If I put my hand over it, you'll see the charge is coming back. Since the wire is small, we don't see a great change on this, but we can get 700-800 volts, and I can discharge it, 0 it, put my hand on the wire, and now the charge is coming back. To demonstrate this, you see that on the 200 volt range here, we are past 200 volts. So voltage-sensitive devices would have a real problem with this length of wire. We'll take an ionizer over here, and we will turn the ionizer on and watch the discharge rate. You're also hearing it on the radio, so I will shut the radio off. You see, it takes quite a while for it to come down. Ionizers can give you a false sense of security because they do not discharge as fast as the charge plate monitors indicate. It's taking quite a while to get below the 200 volt level. And of course, if I touch it in any way, with my hand, with an ESD glove, much worse, you're generating a lot of charge. So it is very difficult to prevent charges from being generated that will affect voltage-sensitive devices. One of the things that's most often asked is how far away do you have to be from ESD-sensitive product. This demonstration will give you a feel for the different types of discharge and the distances away. 1 meter rule was in the military early. It has been removed. But staying a good distance away if you're not grounded is a good practice. But when you're actually working on devices, we will take and show you how far away a charge can actually transfer itself to any material. I have the Teflon sheet here again, and it's sitting on top of the case of the power supply, which is grounded. And I will connect myself up to ground again for the wrist strap, because that's just good ESD practice. And I will turn my radio on, put it off station, and the demonstration is going to involve this gold ball, which is a ping pong ball plated. There's a neon bulb in here connected to one end of it. The other end comes out to a rod which I'll be touching. I'll be holding it on this end, and I'll be holding it on this end, and we'll see the discharge coming off the sharp edge here, the small edge, and off the gold-plated ball. The Teflon is charged again by rubbing it, and as we said earlier, capacitance is an important factor in the amount of damage that can be done. In this case, as I lift the Teflon up, the field now is free to go to other objects because the capacitance has changed. And when I take the gold-plated ball and I approach the material, you hear an arc. That arc is a good distance away. That's an actual arc that can damage energy-sensitive devices and voltage-sensitive devices. If I repeat the experiment, and this time I use the very small end, and I come in, you should hear some discharges at a further distance out. That discharge is not as severe as the discharge off the gold-plated ball face closer. That shows you that at a distance, if you get corona or fields, you can damage a voltage-sensitive device from that. To show you the effect of capacitance now, we'll leave the Teflon on the surface that's grounded, and we'll bring the gold-plated ball near it again. Have to be very close to get a discharge. And you can see, picking it up, I'm getting discharge a long ways away. That's the change in capacitance. I can do it for the other end also to start it back at an even point. I'll go with the narrow point here, which is the worst case as far as discharging at a workstation goes. I'm about an inch away. So what this shows, about 11 inches out, 12 inches out, is the distance that a highly charged object will discharge to the circuits. So if you stay further than that distance away, you're going to be fairly safe for protection of devices. What we have talked about is the voltage-sensitive and energy-sensitive devices, packaging, the rules that you need to follow for grounding at ESD workstations. The voltage-sensitive device can be damaged by fields. They're the hardest to protect to. They need special consideration. The energy-sensitive devices can be protected by following all the normal rules. The types of materials we talked about was the metallized foil, the pink poly, and the metallized material. The foil material is the best shield, and for voltage-sensitive devices that need full protection, we package it in pink polyethylene, then we put the pink polyethylene inside the metal foil bag. That gives full protection. The metallized bag, as we've shown just in these last demonstrations, will transfer charge very rapidly, as will the metal foil bag. You have to be extremely careful on where you have those bags and to remove them in the workstation. The pink poly bag dissipates the energy in the material, discharges the charged surface slowly. That is the ideal material to have. If you follow the rules that we have set up here, we will not have a problem with electrostatic discharge damage of any of the components. The voltage-sensitive devices are going to take special care, special consideration, and we need to be very careful with those devices. Before we move on, there's one more issue we have to cover, and that's the issue of moving air. People believe that moving air tribocharges. The air does not have sufficient energy to cause ionization of a surface or charging of a surface. What we have here is a box that has a 100-pound weight on it with a closed orifice, and as you know, with the bicycle pump, when you pump up your tire, the air gets hot. But if it comes back to the same temperature as the temperature outside the box, the speed of the molecules in the box and outside the box are the same. In other words, the still air velocity inside the box is the same as the still air velocity outside the box, and it's a supersonic speed. The sum of the velocity is zero. In other words, all the molecules are bouncing off of each other. The reason it supports the 100-pound weight is that there are more of them in here than there are out there. And because there are more of them in here, when you open the orifice, they come streaming out because they have a longer distance they can go before they bump into another molecule. But they're going at exactly the same speed. Therefore, they have as much energy stored in the velocity of the mass as they have out here. And this time, when they're going out through there, you feel that sum of velocities in one direction as air blowing onto the surface. But still, it's clear that from these two numbers that the energy is the same. Therefore, the gases flowing out of a nozzle, air blowing over a surface, will not tribocharge that surface. Since it doesn't tribocharge that surface, no electrons are lost or gained by that surface. And therefore, moving air is not a danger to any electronic devices. At Lockheed Martin, we use this electrometer system to measure the charge at the workstation to determine if there's any potential for damaging sensitive electronics. We do not use handheld field meters to survey insulators and other objects in the area. To demonstrate the unreliability of the reading that you get from one of these meters, the setup here has a Teflon surface that has a plate sitting on top of it, and everything is at zero. The meter is reading at zero. The meter is at the zero distance, or the 6-inch distance, which is correct for reading the voltage on there, zero. And now we're reading approximately 1,700 volts on the electrometer on a 5 picofarad capacitance, and the meter does not show more than 400 volts. We put it back again, and the meter changed very slightly. And we can see that there is a charge there as we bring the meter down, but it has to be at the correct distance to give the reading. Therefore, to really understand how much charge is on a circuit board, we use this electrometer system to measure the charge on the device itself so we can get an accurate reading and not misled by the potential damage that could occur in operations here at Lockheed Martin. If we look at direct discharge, we see that if we have a transistor type of device, which is represented by a junction, which can be a diode field effect, if we have a direct discharge to that, whether it's damaged or not depends on the amount of energy in that discharge. If we have a charged surface here that is inducing a charge through the capacitance, the charge will run through this device. It won't be sufficient to hurt the device. With the field effect transistor, the MOS devices that do not have any protection, the gate oxide, if you take and throw an arc onto any pin leading to that, that voltage will be exceeded and the device is damaged. This case also, if you bring a charged surface near it, the capacitive coupling, if it exceeds the voltage of the device, you will damage it. Most likely destroy it because of the narrow range of voltage that it takes to cause damage. If we look at MOS devices, metal oxide semiconductors, that most of the computer chips are now, and a lot of the other electronics, there's protection circuits. These protection circuits are represented by diodes, and any field induced onto these devices will just run current through the diode protection, and the gate oxide voltage will not be exceeded. The device is protected. Lockheed Martin has several pieces of information concerning ESD. The first brochure here is our basic awareness training that's given to all the people that take ESD awareness training. The second item is a list of untrue statements. This has been created by the Lockheed Martin Material and Process Control Engineering Lab, and these statements are some of the common misconceptions that are in the industry. And people can call our department to find out what is going on with the different statements if they need to have them elaborated. The other piece of information that explains what is going on here at Lockheed Martin in way of controls and the damage that can occur when you have ESD problems and no controls is this Lockheed Martin Electrostatic Discharge Handbook. And there is a sheet of information here in how to order that. If you call Process Control Engineering, we can give you that information.